Hello everyone. In the last video we built a half adder that adds two 1-bit numbers. But what if we need to handle carry from a previous addition? That's where the full adder comes in. In today's video let's learn how we can design a full adder that adds three 1-bit inputs. Can add three 1-bit inputs, let's call them A, B, and carry in, let's call it Cn, and produces two outputs which are the sum, S, and carry out, let's call it. So the intention of this is to see what is a full adder circuit. So let's start by a truth table. So a truth table will contain three inputs A, B, and Cn, and it will produce two outputs which are the sum and the carry out. So since we have three inputs, the number of possible combinations of inputs are 2 to the power 3, which will be 8 possible combinations of inputs. So let's start listing them. So we have 0, 0, 0, or 0, 0, 1, 0, 1, 0, 1, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0, and lastly 1, 1, 1. The first row, 0 plus 0 plus 0, the sum is 0 with carry out 0. Second row, 0 plus 0 plus 1 is 1 with carry out 0. 0 plus 1 plus 0 is 1 with carry 0. 1 plus 0 plus 0 is 1 with carry 0. 0 plus 1 plus 1, we learned that 1 plus 1 is 0 with carry 1. 1 plus 0 plus 1 is 0 with carry 1. 1 plus 1 plus 0 is 0 with carry 1. And lastly, 1 plus 1 plus 1 is 1 with carry 1. So next, let's derive the expression for S from this truth table. So we can look at the min terms where S equal to 1. We have this row, S equal 1, this row, and the last row. So let's start with S. S equal, from this row we have A is 0 and B is 0. So we have A prime, B prime, and Cn is 1. So we can write Cn plus. The second row we have A is 0, so A prime, B is 1, so B, Cn, plus. Third row we have A is 1, B is 0, B prime, Cn prime, and then the last row where S is 1, we have all 1, so it will be A, B, Cn. So now let's do some simplification. So S will be equal to, from the first two terms, let's take A prime common. We'll have B prime Cn plus B Cn prime. And then the second two terms, we can take A common. We'll have B prime Cn prime plus B Cn. So this will be equal to B prime Cn plus B Cn prime. This is one XOR the other one. So B XOR Cn plus A. Similarly here we have B prime Cn plus B Cn. This will be one XOR the other one. So B XOR Cn. Now let's look at, we have A prime multiplied by specific term plus A multiplied by the same term. So this is also one XOR the other one. So it will be A XOR the whole second term, which is B plus Cn, with a circle to represent the XOR. So this will be equal to A XOR B XOR Cn, because the order doesn't matter. So this is the final expression for S. Next, let's derive C0 from this table. So we can look also at the terms where C0 is 1. It happened to be the last four rows. So similarly, I'm going to do this quick because we know the idea now. So C0 equal, from this row we have A prime B Cn plus second row where C0 is 1, we have A B prime Cn plus, from here we get AB Cn prime plus the last row we get A B Cn. Now C0 will be equal to, from the first two terms we can take Cn common, so we'll have A prime B plus AB prime, and then the last two terms we can take AB common, we'll have Cn prime plus Cn. So further will be equal to Cn A prime B plus AB prime is one XOR the other one, plus Cn prime plus Cn is equal to 1 from Boolean algebra, complementary law. So now this is the same as ACN or BCN or AB. So this is our final simplified expression for C naught. Lastly, after we derive the expressions for S and C naught, we can start building our circuit. Let's start by building S. So for S, we have an XOR, and we have three terms. So the output is to the left, which is S, and this is an XOR, and we learned that the XOR symbol can be represented like this. And then it has three inputs, A, B, and Cn. So that's it for S. So now for the second term, let's design our C0. So C0, we have three terms and they're separated by plus, and plus stands for OR. So this output will be C naught, and an OR gate will be represented like this, and it has three inputs. The first term is ACN, second term is BCN, and the last term is AB. And we already learned that when we have multiplication, we can produce this by using an AND gate. So the first one we have ACN, we can take A from here, and this curve means those lines are not connected. A, and this is our Cn. The second gate we have BCN, we can take B from here, Cn from here, and then the last one we have AB. So we can take A from here, not connected, not connected, and B. Okay, so this whole circuit here is our full adder circuit. And indeed, it takes three inputs, which are A, B, and Cn, and produces two outputs, which are S and C naught. Thanks for watching. Hope this was helpful.